energy density of a magnetic field. Consider a length L near the middle of a long solenoid of a cross-section area A. The volume associated with this length is AL. The energy stored by the length L of the solenoid must lie entirely within this volume, because the magnetic field outside such a solenoid is essentially zero. Moreover, the stored energy must be uniformly distributed within the solenoid, because the magnetic field is uniform everywhere inside. The unit volume magnetic field, called the magnetic field density UB, equal to total energy stored in the solenoid divided by its volume. UVB equal to half I squared. We have proved before. And we know L over I is mu 0 n squared A, and we get that before too. And B in the center of the solenoid is mu 0 n I, where n is the turns number per unit length per meter. Now we do this one. This one, we put this one inside, half L squared, and that's it. And we find out, okay, L over I, this is L over L. Big L over small l equal to mu 0 n squared A. We put this one inside. And A cancel out. So we write it mu 0 squared n squared I squared over 2. This is mu 0. Y squared? Now we have another mu squared here. Okay? We wanted this one. Why we want to? Now look at the B. Mu 0 n I is B. So this is B squared. So we get UB, the magnetic energy density, equal to B squared over 2 mu 0. This is formula you have to remember. Okay. This equation gives the density of the stored energy at any point where the magnetic field is B. Even though we derive it by considering a special case, the solenoid, equation holds for all magnetic fields, no matter how they are generated. The density of stored energy at any point where the magnetic field is B, where the UB equals half 1 over mu 0 and B squared, is compatible to UE equal to half epsilon E squared, very similar, which gives the energy density in a vacuum at any point in the electric field. Note that both UB and the UE are proportional to square of the appropriate field quantity B and E. And we will prove it, okay? They are equal, okay? Sample. A long coaxial cable consists of two thin walls concentric conducting cylinder. Now, this is one, this is the two. They are concentric. Okay. The inner cylinder carries a standing current I. This is one I. The outer cylinder providing the return path for that current, the outside. Okay. The current set up a magnetic field between the two cylinders. Now this is between the two cylinders. Question A. Calculate the energy stored in the magnetic field for a length L of the cable. Now, we want to find the energy stored in the cable. The length is L. Now, what we do, now we do this one. First, we find the magnetic field. How do we find? We see, we use the Ampere's law with the integration B dot ds equal to mu 0 r. Now we take this special case, this is location is R. The thickness is dr. Okay, then the b at this point in this very tiny area is br, this side, 2 pi r. Why? Because b is, by symmetry reason, everywhere is the same in magnitude, and direction, okay, is along the ds. So bds, when integration, the b take it out, okay, and ds is 2 pi r equal to mu I net. I net just the current inside, okay? Okay. So then the ub equal to b squared over 2 mu. We put this one inside. We get mu 0 I squared a pi squared r squared. It depends on the location r. Different r, you have different energy density, okay? UB is a function of R. So when we do the total energy store, we have to use the integration. We take this small cylinder, the radius is R, okay, the length is L, and the thickness is dr. So this dV equal to 2 pi r L, the surface area of this cylinder, multiplied by dr. So this dV. And then we do the integration. Integration is from where to where? The question is, total is from A to B, right? And it covers whole the area. So it's from A to B. The leftover is very simple integration. I'm going to do it. So the answer is mu 0 I squared L 4 pi log B of A. We can do it different way. We're going to see UB equal to half L I squared, okay, and that we will find that we get the same answer as this one. Okay. Question B: what is the stored energy per unit length of the cable if A is 1.2 millimeter, B 3.5 millimeter, and I is 2.7 ampere? We just put the number inside. Very simple, okay? Per unit length, we put the L over here. That's the energy stored per unit length is equal to mu 0 I squared 4 pi log B over A. We put the number inside, we get the answer. So about 780 nanojoule per meter.